Hey everybody, Sergeant Schultz here, and this is a AP Stat lesson on residuals and residual plots that you'll need your calculator in this lesson. So let's go ahead and use your information from board problem 17 to answer the following questions. So let's see, I think I have the equation right here from board problem 17. So on this, let me get rid of this here. Y was their height right there, and then X was what was their age in months right there. So here we have Darren is 48.12 centimeters tall. You're going to plug that in right there, and you're going to solve for his predicted age for X right there. So if you plug it in and do your math correctly, I think you're going to get choice A. Alrighty. Alright, so let's go ahead and take care of the residuals here, okay? Residuals, how far off your predicted value is from your actual value. Remember, your predicted value you get from your linear regression line, your least square regression line. Okay, in other words, it's your observed y, the y that you observed it to be, minus the predicted y that you'd plug in your answer there, your equation that you get your least square regression line. I'm having a hard time talking through this one. Okay, so it's y minus y hat. Okay, it's always y minus y hat. That equals your residual. It'll make sense when we get into this. Okay, so here we go. The Giselle score test is an aptitude test. So does the age at which a child begins to talk later predict the Giselle score? So here's a study of 21 children and the age in months in which they spoke their first word, along with the Giselle score taken at a later time. Sorry, it's at the end of the day. You guys have been teaching all day. This table is taken from example 314 on page 168, so pull your calculators out, and I want you to put all the ages in list 1, all 3 columns of the ages, and put all the scores in list 2. And go ahead and pause it, and I'll wait for you guys to pause it. Alright, now you're done paused it, so what you're going to do now, you got list 1 is your age, list 2 is your score. You're going to go ahead and make a least square regression line and a scatter plot of this. Okay, whoops, I went a little bit too fast. What I want you to do, you guys, is go to stat and then calculate, and then let's see, can I help you with that? Stat, calculate. So stat, calculate, whoops, and then do number 4. Okay, which is linear regression. Okay, linear regression. Okay, and it'll do something like ax plus b. I think that's what it says, plus b. Okay, and I want you to do list 1, comma list 2, comma y sub 1. Okay, so list 1, comma list 2, comma y sub 1. All right, let me get that over there. So list 1, comma list 2, comma y sub 1. Okay, and y sub 1 is found in vars, which stands for variables. So hit vars, hit scroll over to y vars. Okay, and then it's under function, so hit enter and then enter again, and you'll see y sub 1 appear. Okay, so then and then hit enter one more time, so your linear regression line will come. And what that does, it not only gives me the equation for it, but it stores that equation in y sub 1. And we're going to need that for later. So you're going to get a graph that kind of looks like that. Okay, so then hit graph. Okay, and then hit zoom stat, which is zoom number 9 if you're using a TI. Casios, I don't know how to do these on the Casios, you guys. I'm sorry, but the TI 83s and 84s, that's what you do. Okay, and this scatter plot right here, the open circles equals 2 children. So right here, there's 2 children right here, and there's 2 children right here. In fact, they were children 3 and 13. They matched up with the same scores, and 16 and 21 also, excuse me, matched up with the same scores. Excuse me, and I don't know how to do that in the calculator. I don't know how to distinguish those ones right there. All right. Excuse me. So explain the negative association. Okay, well, the negative association means this, you guys. As the older they get before they speak their first words, in general, the lower their Giselle score is. Okay, so that's what they're asking for. Kids who begin to speak later tend to have lower test scores than the earlier testers. Okay, look, there's a couple of outliers. Here's child 19 up here. Here's child 18 right there. All right, so The correlation describes both the direction and the strength of the linear relationship. And then here you should have gotten negative 0.64. Okay, in fact, your equation should have been this, okay, when you did your equation. So double check, make sure you get the same numbers I do so you can get the same things I do when we talk about residuals in a little bit. All right, so let's take a look at child 2, you guys. Child 2 was at age 26 months, and he scored 71 on the Giselle score. Okay, so what I'm going to do is, this is the actual score right here, and then to get the predicted score I plug in 26 into my prediction equation right there. So I plug 26 in right there, and the predicted score gets me 80.5718. Okay, the residual is the actual score y minus the predicted y right there, so it's going to be a negative 9.57. Okay, let's try it again with child 1. Okay, so they first spoke at 15 months. This is the actual y. Find the predicted y. You plug it into this equation right here, and then you subtract those two. Okay, and then so there's the predicted y, 92.97. So I'm going to take 95 and subtract 92.97, and I get a positive 2.03. Okay, so that's what residual is right there. And then there's all 21 residuals right there. Now those residuals would have a sum of 0 because it's the average of them all, you guys. And then when you average them out, some are positive, some are negative, but that prediction equation gives you the average of them all, and they should average to 0. So so this one doesn't because it's due to round off error right there. So all right, so let's go ahead and do this in our graphing calculator. Steps to graph this in our calculator. And you can stay, Stephanie, if you want. I'm just finishing this recording right here. Okay, honey. All right. I'll be done in 5 minutes, sweetie. Okay. All right. Okay. I had a kid come in for some help there. Okay. So steps to graphing a residual plot on a graphing calculator. So here we go. Now that you have your scatter plot and your least square regression line already in your calculator, go ahead and press Stat and press number 5. And way down at the bottom is Setup Editor. I don't know why you have to do that, but you do. So press Enter. Okay. And once you do that, then press Stat again, press Edit, and then scroll over to List 3 and make your cursor go all the way up to the top where it's in that little box of List 3, right up at the top, and highlight that, and then enter in List 2 minus, and now this is like f of x, except it's y sub 1 of list 1. Okay, we're plugging all the list 1s into y sub 1 equation. This is my my predicted y's. Okay, so here's my actual y's, here's my predicted y's. Okay, so list 3 is going to be programmed for list 2 minus y sub 1 and list 1 of y sub 1. Then press enter, and then all of a sudden you'll see all the residuals scroll down in list 3. All right, now when you do that, then go back into stat plot, which is above y equals, so second function y equals, and deselect your regression equation. So you're going to go over into, scroll into y equals, and then when you do y equals, put your cursor right on the equal sign and press enter, and you'll see your little equals bar get kind of bigger and skinnier, and that means you're deselecting it, so it won't graph that anymore, and then press enter. Okay, and then now go back into stat plot, turn stat plot 1 on, and list it with list 1 and list 3. Okay, graph it, and then hit zoom stat to graph your data right there, and you should get a graph that looks like this. All right, and then here is the x-axis, and that's my residual line right there. This is called a residual plot right there. Okay, and then so now if you calculate the sum of the residuals, they're in your calculator in list 3. So if you did a one variable stat in list 3, you can see that the mean of those is close to 0. In fact, I get this number 3.857 with it to the negative 12. That means the decimal goes to the 12 places to the left. All right, so here's a side by side. Here's the residual plots, and here's the scatter plot of all the data right there. All right, so this residual plot, you know, it's kind of even right here, but it kind of gets kind of weird when you get out here right there. So it's not very accurate. So residual plots help determine if a regression line is a good fit for your data. So here's some examples. So put your pencils down and just watch for a second. This residual plot is an excellent plot to do a linear regression line because everything's evenly spaced above it and below it. a linear regression line would be a great representation for this residual plot right here. It's a nice uniform scatters of each point, okay? And then on the regression line. These residuals have a curved pattern, so a straight line is not an appropriate model. Okay, it's inappropriate. It wouldn't be, so a linear regression line wouldn't be such a good model for that. I mean, you could do one, it just wouldn't be a great one. And this one here, you know, it's kind of scattered a little bit, and it starts kind of, you know, waving. It gets like a big fan out here. It gets bigger and bigger. So it has, it gets more spread, and so your prediction would be less accurate when X gets large. So it might be okay over here, but it would be less accurate when it gets large right there. Okay, we want it to be nice and uniform. All right, and I passed a handout of just pictures of all those right there, what I just did. All right, so child 18 and 19, they're both outliers. 18 has more influence on the data because it's much further out in the X direction than child 19, and also 19 has less influence because many other points with the same X values are around child 19. They're around, you know, 19 is just above it. They have similar X values, so it anchors down 19 a little bit better. So think of a teeter-totter out there. You know, here's child 18. It's pulling it down, you know, because he's farther out on the teeter-totter, so it pulls the line down quite a bit. So what we're going to do is we're going to take out child 18. So before we do that, calculate R squared. So that should be when you did your linear regression, okay, and it should be in your R squared, and you should get R squared to be 0.41 when you did linear regression, line 1, line 2 with the y sub 1. Okay, so that's with all the data in there. This says that the age at which a child begins to talk explains about 41% of the variation on a later test score of mental ability, and could be of interest to some parents. Parents would think, you know, that's might be a pretty good influence on their kids right there. So let's take out child 18 and calculate R squared again. Okay, so go back into stat and edit and take out child 18 in both list 1 and list 2. Delete them both, okay? And then go do a linear regression calculation again. All right, you should get R squared to be 0.11, which is 11%. So the apparent strength of the association was largely due to an influential observation right there. All right, so this is what you might want to say when you're taking the AP test. They want to hear you say something like this. So the researcher that did this, she must decide whether child 18 is so slow to speak that the individual should not be allowed to influence the analysis, and if she excludes child 18, much of her evidence, it drops away for a connection between the age and the child when they start speaking. It vanishes. So if she keeps child 18, she probably needs to calculate some more kids. You know, instead of 21 kids, she probably do 50 kids and see if she can get her a better approximation of a linear regression line. Alrighty, so let's see. That's what happened when we took out child 18. It gave me that regression line. It made it less accurate right there. Anyways, why don't you give it a shot with that homework assignment? Take care, everybody. Thanks for hanging in there.